चले जाएं।
So, good evening, everyone. I guess you all can hear my voice. So, I have a bit of cold, so my voice is not problematic right now. Just a second. So, welcome to today's session, that is problem solving session, week 10 of this course, Semiconductor Devices and Circuits. And my name is Shomnath Bhattacharjee. I am currently pursuing my PhD at IIT Jodhpur, and there are only two sessions remaining that will be also that is also scheduled for the next two Sundays from 7 to 9. So up until now in this course we have already learned about the BJTs, MOSFETs, and finally in the last week we have learned about the MOSFETs, that is metal oxide semiconductor field effect transistors. And we have already learned the basic of these like MOSFETs. Right now we will understand how we can scale the MOSFET down, that is different types of scaling, how we can characterize this MOSFET, and based on that characterizations, how we can extract specific parameters like the key parameters specifically like the mobility, the VTH, the subthreshold swing, subthreshold slope, trap interfaces and those things. So we'll learn about that. So first we'll start with, so before scaling, we need to know there are like several like key parameters we have like not learned until now. So those are the trap charges. So what is a trap charge? So up until now, our basic assumption was that a basic insulator like this. Let me draw it in a more better way. So up until now, our insulating layer, what we have like assumed is that this insulator is a perfect dielectric material. A perfect dielectric material. So what does it mean? That there are no kind of a charge carriers or even like no kind of electrical current can flow through it. So we were assuming that there is like we know that there will be like there will be no current flow through it, but we were assuming that there is exactly zero current flow through it. But in reality, there is nothing called a perfect dielectric. Because of that, what is happening in this kind of a insulator is that there are very small amount of charges inside this insulator. So these are based on different phenomena and different cases, but there are different kind of a charges, and that's why this is not a perfect dielectric. So there are several phenomena like there can be some kind of a mobile ions. So, like these mobile ions can be due to like can be present due to clean room conditions. So, when you are fabricating this device, there may be not enough cleanliness in the room, or some dust particle or some iron particles. So, because of this, there can be like several kind of a mobile ions inside this inside this layer, that is the dielectric material. When you are fabricating this dielectric material, there can be these kind of a mobile ions can be introduced, and based on that there can be impurities in this dielectric materials. Second, so there can be trap charges as well. So what are trap charges? Just a second. So what are these trap charges? Trap charges are like mobile electrons and holes that is able to move based on different temperature applicability. So these can move at a higher temperature, and because of these trap charges inside this oxide layer or the insulator layer, they will move when the device is getting heated up or you are applying a voltage, and because of that these mobile electrons and holes will move, and based on that there will be a slight bit of current flow inside this. Apart from that, there can be interfacial trap charges. So the difference between these interfacial trap charges and the oxide trap charges are that in the interface, so it can be a metal to insulator interface and insulator to semiconductor interface. At both the interfaces, there can be a mismatch of the surface, and due to this surface mismatch, there can be trap charges. And another thing is the fixed charges. Now, what are the fixed charges? So, up until now, we have learned about the mobile lines that several mobiles and are getting like what do we say like during fabrication, these are getting introduced to the oxide layer. Then there can be trap charges on the interfaces, like this interface as well, and also inside this. But these fixed charges are just a sec, are very close to the surface close to the interface, but these are due to silicon wafer processing. So what do you mean by processing? Processing is like while cleaning it or while oxidizing it, there can be fixed charges, introduction of fixed charges, and based on this, there can be several issues. So these kind of trap charges and ions, what do they create is that they create a very small amount of current inside this insulator, and based on that, there can be a leakage of current or a very small amount of current, which is making this like insulator not a perfect dielectric. So it is not a perfect dielectric. And a specific thing to know is that based on this interface trap charges, what happens is that it changes the interface capacitance, and based on that we can say that the amount of ss increases. And what do you mean by ss increase is that the device gets slow, that is slows down the MOSFET. So the device will turn on slow and the device will turn off slow as well. Another important factor to understand before the scaling thing is that is body bias. So what is body bias? So previously what we were seeing that we were considering that VBS or VSB, whatever you say, is zero. So we were considering it as zero. Why? Because if you were considering it at zero, then like effectively your device have only three terminals. So that's why in most of the cases we say that a transistor is a three terminal device. But as like it is also another terminal which can be implemented to get more sophisticated results. So based on this body bias, what we can do is that we can modulate the threshold voltage. So the minimum amount of voltage required to turn on this device. So we can modulate this threshold voltage based on this like the base bias. So how we can do that is that so the thing to turn on a the voltage needed to turn on like a transistor is VGS, which we can write it as VGB plus VBS. So based on this body bias, the transistor operation will change. And so I am just omitting all the calculations and those things, but the essential thing to know is that if the VBS, that body to source voltage, is positive, the amount of VTH will decrease. So VTH will decrease, and if the VBS is negative, the VTH will increase. So in most of the cases we need a very low VTH. So this is a very good thing to know that if we are increasing the VBS, that is VB minus VS, if we are increasing that, so we can increase the VB value or we can decrease the VS value, and based on that we can decrease the threshold voltage as well. So now we'll move to how to scale transistors. So the main thing is that within a very small amount of area or a small amount of space, we need more and more transistors to get a very like a high what do we say, like to get a very high quality of application or a very complex application, and based on that we need more and more transistors. So how to do that? So our main aim towards scaling is that we need to scale down a transistor. So there's few like physical variables which can be scaled down. Those are obviously L, W. So W and L can be easily reduced to reduce the physical size of the device, and we can also reduce the TOX, that is the oxide thickness, and based on that we can reduce the total height of the device as well. But like these things we can just directly reduce them and try to get the same like operation from the previous device to the new device. So there will be two types of scaling down. The first type is the constant field scaling. So what happens in a constant field scaling is that the total electric field is constant. So if we need to make the electric field constant, what will we do? That we'll just reduce the W, L, T ox, everything with the constant, what do we say, like a constant value that is alpha here. And based on that, we need to reduce all the voltage values as well. So we will reduce with the same coefficient, and based on that, the total electric field will remain the same. Another technique is that constant voltage scaling. So in constant voltage scaling, it is very likewise that what we'll do is that we'll just make the voltage values constant. So if we are trying to make the voltage values constant, what will we do is that we'll just reduce this similarly. Sorry, it will be this. And we'll just increase the electric field with this alpha variant. So what will it make? That it will make the voltage values constant, although we have already physically reduced the size of the device. Now, so based on these kind of a scaling down, there will be key changes to the key parameters, that is the mobility, the VTH and everything. So now we need to learn how much these thing, the change in W, change in L, change in T ox, changes these kind of a values. So we need to know the effect of scaling down on threshold voltage. So essentially the formula what we'll get after this is that when the device was longer, so this would look like this, and the formula will come out as XT by 2C ox 1 minus L dash by L. So L dash and L is the this difference. So the channel area, this is the channel area, and based on this is the L dash and this is L. And now also another thing to know is that for a shorter channel device, L dash is much smaller than L for a short channel device, that is when the channel is reduced. But for a long channel device, this trapezoid kind of a structure looks like a very normal rectangular structure. And based on that, we can directly get that if we reduce the channel length, VTH will also reduce as well. So based on this, we know that if we reduce the channel length, the VTH will reduce, and also we get that if we reduce the channel width, the VTH will increase. Now, our ultimate aim is to get a very reduced amount of VTH, as we need a very reduced amount of VTH. So we can certainly say that the aspect ratio or the W by L should increase. So it can be done with what? That we can increase the W and reduce the L. So if we are reducing L, we have to make the W constant, or even better, if we can just increase the value of W. So by these two factors, W and L, we can control the amount of VTH reduction or increase. So these are the basic thing. And also there is another limitation as well. So like we can't indefinitely reduce the value of W and L. So apart from the physical parameter that we can make us this smaller W or this smaller L, there is another thing that is the, so there is a limitation which is due to effect called carrier multiplication. As the channel gets very smaller, so there's a effect called carrier multiplication effect. Everything can be like mathematically deducted, but like I am just omitting those parts. So apart from that, there is another factor that is called the parasitics. The concept of parasitic capacitance and those things comes from here actually. So what is parasitic? Parasitic thing is for a long channel, we know that the gate voltage controls the barrier. So control the barrier to charge injection. So we know that based on the gate voltage, the device performance changes for a long channel. And now when the channel is reduced, so for a short channel, what happens is that the drain voltage influences the barrier. So our main control factor was the gate voltage. So if we are reducing or increasing the gate voltage, and based on that, the transistor was operating. Now what happens with a very short channel device is that the drain voltage now influences the barrier, and based on that, what happens is that the gate loses control of the device. Without even change in gate voltage, even the gate voltage, if the gate voltage is zero, there is a change in the barrier and the charge injection behavior of the device, and that is called, so this phenomena is called is DIBL, or drain induced barrier lowering. So when the channel is very small, and based on that factor, what happens is that the drain voltage influences the barrier to get lower, and there is more charge injection due to that. So this factor is called the DIBL, or drain induced barrier lowering. Now we'll move to various things called the leakage currents. So as I have already told that the insulator is not completely like a complete or perfect dielectric. So based on that, there can be various leakage currents, and these currents are called leakage because it shouldn't supposed to be there. They are not supposed to be present at this insulator layer, but they are present, and because this is very small to the operating currents of the devices, that is why they are called the leakage currents. And so there are several kinds of leakage currents. So the first one is the gate leakage current, which is the most common thing in like the fabricated transistors. And another is the drain source leakage current. So what is a gate leakage current? So what are the, just a second. So these kind of a gate leakage current mainly can be like mainly can like build up because of like several kind of a cases. So the primary case is the Insulator leaks the charges. So what we have already discussed, that can be based off due to sorry, SCLC or the space charge limited currents. They can be due to various kinds of tunneling through the insulator layer. They can be based on hopping transport of the trapped charges, or they can be from mobile ions, as we have already discussed. So how to solve this issue? So how to solve the issue of this kind of a gate leakage? The main way to solve this thing is by using high K dielectrics. Usage of high K dielectric is very much necessary to reduce this leakage. Now, moving on to the next thing, that is the drain source leakage. So these can be due to like several factors, that is like the diffusion, generation of charge pairs. One of the unique thing is the band tunneling. So from a band to another band tunneling, direct tunneling of charge carriers. And another thing is called the GIDL, or gate induced drain leakage. So due to this scaling factor and everything, there is another phenomena that is called the gate induced drain leakage, and because of this, even at a like voltage very low, there can be a drain leakage due to this induced gate voltage, and so that is called the GIDL, or gate induced drain leakage. So these factors can also be like solved with the high K dielectric in those cases. And I'm sorry. Yeah. So now these were the factors that we have already learned, that because of these are the like, what do we say, like uh, we were assuming that insulator is not conducting any current, or it can't conduct a current, or it like it is blocking the current totally. So because of that, so there were several miscalculations, and based on that we are assuming that there is a leakage current, and these currents can be formed from both the sides. So it can be from the gate side, that is the gate leakage, and it can be also drain and source leakage. Apart from that, what are the effects on different key parameters based on this like reduction or the scaling down of these effects? So these were the things. Now we'll move on to the different parameters extraction from direct characterization of these devices. So these devices are directly characterized by, so like by just directly connecting the gate, source and drain terminals to a SCS, that is a semiconductor characterization system, or also like SPS, semiconductor parametric system. So these are like different like devices that can be used to characterize these devices. So for a MOSFET, we generally get only three kind of a characteristics. The first one is the transfer, that is the variation of IDS with respect to sweeping VGS. So in this case, what happens is that we are sweeping the VGS values with respect to, and we are also recording the value of IDS when we are just giving a constant VDS. So we are giving a single VDS value, and based on that, we are just we are sweeping the VGS value. And after recording, these kind of a values look like something like this. So a basic transfer curve looks something like this. So if this is the IDS and this is the VGS, gate to source voltage, the values will look something like this for a certain VDS. And if we are applying a different amount of VDS or a different value of VDS, it can look something like this. So with a VDS of 1, VDS of 2, this will look like this. Now, the second type of, so it's one right, I guess. Second type of characteristics is the output characteristics. That is, we are measuring that variation of IDS with respect to sweeping VGS. Now we are sweeping the VGS with respect to not VGS, sorry, VDS. So we are sweeping the VDS and recording the VDS value. And while we are recording this, we are applying a constant VGS value. Now a plot of this thing will look something like this. And if we are applying IDS, VDS with a single value of VGS1, let's say we have another one. So it can be VGS1 and this can be VGS2. So this is a basic output voltage, output current characteristics. And another thing is that the CV characteristics. So a basic CV characteristics will look something like this. So you are measuring the capacitance with respect to a VGS sweep, and so this looks like something like this, and this may be in picofarad or nanofarad or something like this. So this is in farads, and the plot will look. Just a second, I'm just removing this. This will look something like this. So based on these three characterizations, or based on these three curves of a single device, we have to estimate that what are the key parameters of these devices. So the first key parameter we need to know is that, just a second. So the first key parameter we need to get is that the aspect ratio, that is our W by L ratio. So how to get that? As we have already designed this transistor and we have fabricated this transistor, we already know this value. So this is nothing but the design parameter. We already know this value. So we know the channel width and channel length based on our fabrication. So then the next thing we need to know is the value of VDS. So how to get this value? As we are applying this VDS value to the transistor, so we can directly get these values. So these are the applied parameters. Similarly, VGS is also another applied parameter because we are applying this, and IDS is the recorded parameter. So IDS, that is the value of output current and everything. So this is the recorded parameter. So this is the recorded parameter. So these are the basic key parameters. Then what we need to know is the value of Cox, or the capacitance per unit area. So how to know that? So first, to get the value of capacitance per unit area, we need to check the value of this C. So this C is nothing but only capacitance. But to get the value of Cox, we need to divide it with the capacitance per area. Now capacitance per area is nothing but capacitance divided by W into L. Now we know the value of W by L, and based on that we can get the value of Cox. Now we know the value of Cox from the CV characteristics. Now we know the value of Cox. Now our next parameter we need to estimate is the value of VTH, or the threshold voltage. So how to calculate this threshold voltage? So we need to go to the first plot here, and now based on this transfer characteristics we can plot different values of transfer characteristic directly from the plot itself. So what we'll do is that we'll plot this transfer characteristics but with respect to IDS half and VGS. So why are we plotting like this? So we are just we are just getting the square root of the y-axis and we are just plotting the x-axis directly. So the plot will look something like this, nearly a straight line. And if we are, so from this, the maximum slope, if we are directly plotting this, this value is VTH. So we can directly get the value of VTH from the transfer plot. So from the transfer plot or the square root of the transfer plot. So from the transfer characteristic, we'll get the value of VTH. Now the next value we need to know is the mobility. So how to get the mobility? So now for the mobility, what we need is that we need the value of we need the value of VTH, we needed the value of Cox, we needed the value of W by L. So all these things we have already know. So we can just calculate the value of mobility from these values. Now we need to know the value of SS. Now to get the value of SS, what we need to do is that we have to again replot it, but now on a log ID, so on a semi-log axis. This will remain same, but this plot will look something like this. And based on this, what we'll do that we need to ascertain a decade change in the current. So we need to ascertain a decade change in current with respect to the change in the VGS values. From this, we can get the value of SS, from which we can get the slope and also the swing as well. So both can be estimated from this. So SS can be also estimated from the transfer characteristics. Now, sorry. Now the saturation point, we need to know from where the saturation is happening, and so sorry, just a second. So to get the saturation point, what will we do is that from a certain value of this, we can get this VGS minus VTH point. So from this point onwards, this is the saturation region, and based on this output characteristics, we can directly get the saturation point as well. And we need to also get the value of lambda. So from the value of lambda can be also estimated from here. So as we know, at after the saturation point, the current should saturate, but there's a slight increase in this current. And based on this, so if we can just draw a slope on this kind of a thing, we can get the value of lambda as well. So lambda can also be calculated from the saturation, the output characteristics. Now, apart from this, if we need to get the value of C depth and C interface, so to get this, we need both the characteristics. So we will need the CV characteristics, and also, so to get the C depth and to check it with the if it's consistent with both the curves, will need the, oh sorry, will need the transfer characteristics as well, and the CV characteristics both at the same time. And apart from that, the new things, that the GIDL, that is the gate induced drain leakage, and the DIBL, drain induced barrier lowering. So both of them can be directly, like the leakage, or we can say the leakage mechanisms. So both can be estimated from directly the output characteristics. So how to measure them from the output characteristics? So this is for a single device. Now, no, sorry, just a second. Not from the output characteristics, it will be from the transfer characteristics. So how to get this from the transfer characteristics? In this case, what we'll need to know is that we'll just have to have a different values of these. So with different values of this, so how to get this different plots? So we'll have to apply different amounts of VDS, and based on this VDS change, we can directly calculate the amount of GIDL and DIBL. So both of the leakage mechanisms can be directly calculated from this as well. I'm not missing some. Oh yes, and also, oh sorry, and also NA can be calculated directly from the CV characteristics as well. So these, sorry, yeah. So this part of this is nothing but due to both this, right? CDEP and CIT. So this is one by one of CDEP and CIT, and based on that, we can also calculate the value of NA. Now, so these are the several parameters which can be. So these are the several parameters which can be directly extracted from the curves itself. Now, so just we if we are just basically characterizing the devices and getting these three kind of curves, and we can directly get all the parameters that is required to ascertain the performance of the device and how these devices can be performed. And based on this, we can change the change both the parameters. So these are the design parameters, the applied parameters, and the recorded parameters. Based on these factors, we can modulate all the values, and we can get a certain amount of the required transistor. That if we need a VTH of, let's say, less than zero point 0.2 volt, so we can make it. If we require a mobility of this amount, like let's say a mobility of 60, so we can get that. And based on this factor, based on the scaling factor, based on the applied parameters, and based on the design parameters, we can make a certain transistor that is exactly helpful for our application. So this was it for this this week's classes. So if you have any question, you can ask me, or we'll move on to the questions, like the problems. So if there is no questions, so we'll move on to the problems. Are there any questions?
No, sir.
Okay, fine. So we'll move on to, oh, sorry, just a second. So we'll move on to the problems. Let us consider an ideal in MOSFET with channel length. So these problems are very similar to the problems in the previous week as well, because there are very few amount of equations, and we need to solve this because of like getting the total like understanding of the architecture and total operation of these devices. So we will just repeat these kind of problems as well. So the channel length is 1.25. The mobility of electrons is 650 centimeter square per volt second, and the threshold voltage is 0.65 volts. Now we have to design the channel width of the MOSFET such that the saturation drain current is 4 milliamperes for an applied gate to source voltage of 5 volts. In this case, we also know that Cox value is 69 nanofarad per centimeter square. So we have to find the value of W. We know the value of L, we know the value of mu, we know the value of Cox, and I guess we know the value of VGS and VDS as well. We just need to know the value of W. Okay, do this. It will take a minute, just a minute, I guess. Also, is it like it is given that it is in a saturation, as they have mentioned the saturation drain current. So the saturation equation will be like used here. Maybe I'll just give the solution to this and using these kind of like a structure you can like solve this. So let's do this. So the equation is nothing but id mu n cox by 2 w by l vgs minus vth whole square. So from the equation we know the value of id, right? So id is 4 milliamps equals to mu n is the mobility is 650. So 650 multiplied by cox. Cox is given on, yes, Cox is given. So 69 nanofarads divided by 2 multiplied by W by L. So the value of W by L, just we are just keeping it W by L for now. So we'll just multiply the L afterwards, and value of VGS. So the value of VGS is gate to source voltage was 5 volts and the threshold voltage is zero point 0.6 volts. So this is the value. So W by L equals to, let me just use my calculator first. So this will be 4 times 10 to the power of minus 3 multiplied by 2 divided by 650 divided by 69 divided by 5 minus 0.6 whole square divided by 10 to the power of minus 9. So the value is 9.2134 and we know the value of L. So W will be, L was how much? L was 1.25 multiplied by 9.2134 or 1.25. So it will be 11.5168 microns, or we can write it as 11.5 micron. So this is the value of W. So W was 11.5 microns, whereas the channel length was 1.25 micron. So let's move on to the next one. Question 2. Now let us consider a MOS structure with a P-type semiconductor substrate doped to Na 10 to the power 16 per cc with a silicon dioxide insulator of thickness 50 nanometers. So we know the value of Tox here and we know the value of Na here. Let the equivalent oxide surface charge density be 16 Nc per centimeter square. The metal semiconductor work function difference is 0 point minus 0.8 volts. We need to calculate the value of flat band voltage. So we have already learned about the flat band voltages. So let me just give you a hint. So the flat band voltage in presence of oxide surface cha- charge is flat band voltage VFB is nothing but psi of ms. So psi of m minus psi of s, which is already given here, minus of q of oxide, that is the charge, surface charge, divided by co. So everything is given here. We have to just put the values here. So just put the values and give me the answer. So I'll just put the values. So the value of this is zero point 0.8 volts minus this nothing but 1.6 minus 19 divided by 3.9 into 8.854 multiplied by 10 to the power of minus 14 divided by 50 into 10 to the power of minus 7. So it is nothing but Cox equals to epsilon ox by Tox, and we're just putting the values here. So this will be 0.8 volts minus, just a second, just put the values. 1.6 multiplied by 50 divided by 5.9 divided by 8.854. So the value will be, uh, just a second. So this is 1.6 multiplied into 50 into 10 to the power of minus 19 multiplied into 10 to the power minus 7 divided by 10 to the power minus 14 divided by 3.9 divided by 8.854. So the value is, 2.3167. So let's write it as this up to this, I guess, or let's write it as 68. So the value of VFB is, just a second, 0.8 minus 0.2318, or 0.8, oh sorry, 0.8 plus 0.2318. So this is nothing but minus of 1.03, nearly 1.03. Let's write it like this. Now, what was the problem here was 16 nano, right? Okay, so what I have written here is 16, right? And nano is minus like this. So the value is here. Now we'll move on to the next one, that is question number 3. So for the given,
Excuse me, sir.
yes,
Sir, how to find out the value of COX?
Cox is epsilon ox by Tox. So this was Cox is epsilon ox by Tox. So this is for SiO2, as they have given SiO2 here. So 3.9 is for SiO2 into epsilon naught, that is 8.854 into 10 to the minus 14 divided by, this is the Tox value. So this is the Tox.
Okay, sir. Okay.
So this is from the equation, right? Estimated oxide thickness from the MOS caps. So we are just utilizing that equation in this MOSFET as well. Now, for the given MOSFET, I'll draw the image later, but they have given the aspect ratio as 2, the VDD as 2 volts, K as 100 into microampere per volt square, and threshold voltage or VTH as zero point 0.5 volts. So for this transistor, the transistor switches from saturation region to linear region when the Vin is question mark. So we need to find the value of Vin at which at which voltage the transistor is getting converted from the saturation to the linear. So we just need to find the value. So that is, let me draw the plot here. So here's a resistance just before the transistor, and this is like this, and this is like this. So this is V in, and this is VDD. This is the value of R, that is 10 kilo ohms. This is our V output, and this is the transistor M1. So we are talking about this M1 transistor and everything. Let's remove this M1 for now. So this is the transistor we are working for. This transistor has an aspect ratio that is W by L of 2. The VDD value is 2. So they have already given that this value is 2 volts. They have already given K is 100, and the aspect ratio or W by L is 2, and the threshold voltage VTH is 0.5 volts here. Okay, and apart from that they haven't given anything, so we need to find the V in value at which the saturation region, the transistor switches from the saturation to the linear. So try to solve this. So I'll give you a few hint. So the first thing from this circuit, what we know is that VDD, so this VDD minus VDS is ID into RD, right? So because RD, let's say this is the RD value, and so this is VDD minus VDS equals to ID into RD. So from the circuit we get this, and also, so this is gate to source. So as this is the gate terminal, this is source. We can also write that VGS is equals to V in. So VGS, we know that V in value. So from this we can just directly get the VGS value and we can equate for this. And as the device is in, uh, so device is in saturation. So the value of ID is half of mu n Cox W by L VGS minus VTH whole square. Now you can just directly put the values and get the equation. So from here we can get the value of ID. From here we can get the value of ID. So if we can just equate both, we will get the value of VGS.
But here, two parameters are unknown, right? ID and VGS.
Well,
In the current equation, two
yes.
parameters are unknown.
Yeah, so that's why we have two different equations, right? So this is the basic equation, that is the saturation current equation, right? But this equation, just let me mark them down. Yes. So this equation is a basic equation, that is the current, the drain current equation for the saturation region for a basic MOSFET device. But this is from the circuit. So from
Yeah.
here, we know the value of RD directly. So if I'm just writing this as RD, let's say, so this is RD. We know the drain resistance, that is 10K. We know the value of VDD here. We can directly get ID. So VDS is unknown for you right now, but you can just guess that. What is the value of VDS? So
Yeah, VDS can be it can be basically maximum VGS plus V threshold, right?
yes,
Not
yes,
less than that.
not less than that. But like from the equation, we know that from the question we know that the transistor is getting switching is switching from the saturation to the linear region. So for this condition to satisfy, we know that VDS should be equals to
Equals
VGS
to
minus
VGS. Yeah, right,
VTH. So this
right.
is the case. So if we directly put here, so it will be like VDD minus VGS plus VTH equals to ID into RD. Now here ID is the unknown term and here ID is also the unknown term. And we also don't know, obviously we don't know the value of VGS here as well. VGS, and from here VGS. So we can directly get the value of VGS here by equating these two equations. We just have to substitute the value of ID from both. So
Yes,
we
yes,
can,
get it. Yeah.
yes, try to solve this. So I guess you can get this right now. maybe I'll solve this. So, yes. So from here, we can directly write it as ID equals to VDD. So the value of VDD was how much? Just a second.
I think it will be a huge quadratic equation. So it's simple to solve. Just put value and solve the quadratic equation. If
Okay.
others, I don't know about others, I am just telling.
Hmm.
If nobody,
Yes,
we can
just
move forward if nobody is,
so
has
ID.
the.
So 2 minus VGS is here. VTH was how much? VTH was 0.5 divided by RD is here. And from this, if we are equating this, so 2 minus VGS plus 0.5 by RD equals to 100 times 2 by 2. So 2 can be cancelled out and VGS. Let us do one thing, I guess. Then it will be better. So we are not putting the value here, okay? So we are just getting this value for the time being, and so we are just getting this. Let's do this. So VGS minus VTH, and from here we are getting VGS minus VTH whole square. So this will be the value of RD was 10. So if we are just putting the values, this will be 2 minus VGS minus VTH is equals to ten k. 10k is 10 to the power 4, right? So this will be 10 to the power 4, 10 to the power 4 times 10 to the power 2, 10 to the power 2 into VGS.
That is microampere.
Which one?
10 to the power 2, you are right. K.
Mm, Oh, okay, okay. That means it will be 10 to the power minus 6 here. So this will be 10 to the power. So that is 10 to the power minus 4 and 10 to the power minus plus 4. So these are getting cancelled out. So this will be VGS minus VTH whole square. Okay, so now this is simple. VGS minus VTH and minus 2. So this is a simple equation and it can be solved here. So uh, I guess to better like the better thing would be to just put the values here for now. So this is V in minus VTH was how much? VTH was zero point 0.5. So just write it as this VGS minus zero point 0.5, V in minus zero point 0.5 minus 2 equals to 0. So that means V in minus zero point 0.5. Let's write it like this. So this will be minus B. So let's have a second. Hmm. So this will be minus 1 plus minus B square, that is 1 to 5 B square minus 4AC. 4A is 0 0.5 and this will be C divided by into 2. So this will be 2 and so the value will be V in equals to minus 1 minus 3. So that is minus 4 minus 4 by 2 minus 2 plus 0 0.5 volts. Another one will be 2 by 2 1 plus 0 0.5. So this is minus 1.5 volts or 1.5 volts. So these are the two values of V input. Now, was it
Yeah,
Yes,
1.5, 1.5 volt,
yes,
because it
that's my
cannot go beyond below the threshold voltage, right?
yes. So I was searching for that value here. So that was zero point 0.5. So yes. So sorry, this is the wrong value. So the value will be 1.5 volt. Okay, so let's move on to the next one. That is question number 4. So what do we have here is that now let us consider a NMOS device where the conduction parameter, that is Kn, equals to 0.249 milliampere per volt square. Now they also have given VGS equals to 2 into VTH, where they have also given that VTH is 0.75 volts. What is the current? So they have given the conduction parameter, that is K. They have given VGS is 2 VTH, and there is a very easy one. So the value of ID will be nothing but mu n Cox into no, no. You guys try to solve this, then I'll just give the solution.
Is the conduction parameter is the complete value mu n Cox and W by L, or it includes half also?
Um, what are you saying?
So
So
conduction parameter definition, it is mu n Cox W by L, or
yes, W by L, up to
okay,
W by L, not the half. So the
yeah, okay,
parameter will be half into Kn. Yes.
okay.
So this one is not a very hard one. So this is nothing but half into Kn into VGS minus VTH whole square. That's it. So VGS, they have already given us 2 VTH. VTH minus VTH a whole square. So that will be half into 0.249 into 10 to the power of minus 3 multiplied by VTH square. So that means it will be 0.249 10 to the power of minus 3 divided by 2 multiplied with 0.75 square. So this is the answer. So we just have to put the values. That will be, I guess, 0.249 10 to the power of minus, sorry, 10 to the power of minus 3 divided by 2 multiplied with 0.75 square. So that is 7. How much was that? That was 7 times 10 to the power of, I guess it will be 10 to the power of minus 5, right?
Yes, sir. -5.
Ah,
Yes.
yes. So this is minus 5. So mm, we can write it as 0.07 milliamps. Or it's better to write as, no. Let's write it as this. If we are writing it as microamperes, it will be 70. So that will look like a very huge number. Okay. So let's move on to the next one. So let us consider an N-channel MOSFET which have a mu n Cox of 1 milliampere per volt square, W by L of 10, VTH of 1 volts, sorry, VTH of 1 volts, VDS of 1 volt for VGS of 3 minus 2 sine 4t. What is the maximum current that will flow through this, flow through the device in milliamperes? So we have to find the value of maximum current flowing through the device in milliamperes, and we know that transconductance is 1 milliampere per volt square, W by L as 10, VTH as 1 volts, and VDS as 1 volts. And also we know that this equation, that is VGS equals to 3 minus 2 sine 4t, and we have mu and Cox as 1 milliampere per volt square. W by L, VGS, VDS, everything is given. Yes, everything is given. So it is also another very easy one. Try to solve this. So I'll give some hints to solve this. Sorry. So the first thing to know that we know that the change in current ID is with respect to VGS, right? So to get the maximum current, we need to get the VGS max. Now maximum value of VGS will be 3 minus, sorry, 3 plus 2, right? So that will be 5 volts. So we know that when sine 40 will be minus 1. So this will be the maximum value of VGS. So that is 5 volts. Now when VGS, let's write it as max. This VGS max minus VTH will be 5 volts minus how much? It was 1 volt, right? So it was 1 volt, that is 4 volt, which is obviously, so VDS we know is 1 volt as well. So which is obviously less than this value. So from this we can say this is not in the saturation region. So based on that, we can write that IDS is nothing but mu n Cox by 2 W by L 2 times VGS minus VTH VDS minus VDS square. So if we are just putting the values, mu n Cox was 1 milliamps. So this will be this by 2. W by L was 10. 2 times VGS minus this one was 4. This one was 1 minus 1 square. So we just have to put the values. This is the thing, but 10, 10, 10 to the minus 2, 10 to the minus 2 by 2, 2 into 4, we can do it directly. So this is 8 minus 1, 7. So this is 7, 10 by 2, 10 to the minus 3. So this is 35, 10 to the power minus 3 or 35 milliamps. Yes. So this is 35 milliamps. Let's move on to the next one. So, yes. So let us consider and sorry. So let us consider an device. Let us consider an N-channel device, N-channel MOS with a width of 30 microns and length of 1 micron. They have given the oxide capacitance as 69 nanofarad per centimeter square. Assume that the drain current in the non-saturation region for VDS 0.07 volt is 25 microamperes at VGS of 1.5 volts and ID 65 microampere at 2.5 volts. We need to find out the value of mobility from this device, and the approximation they have suggested to use is VDS is small. So they are approximating VDS is small. So we have already done a similar kind of a problem previously. So what we need to do is that for a small VDS, we know that ID is nothing but mu n C of W by L VGS minus VTH into VDS, because we know that this term, this VDS square term, will be very very small, because of as VDS is small, so VDS square will be much smaller than this, so we can omit that part. So for this, what we can do is that we'll get a single case for this, and we'll get a single case for this VGS when 2.5 volts. So we have to equate both the terms and we'll get the values of the mobility. So try to do this. Hmm. So I will solve this. So this will be nothing but 25 into 10 to the power of minus 6 equals to mobility times 69 into 10 to the power of minus 9. W by L is 30. So 30 uh, multiplied by 1.5 minus VTH. So previously we have done a similar thing with the saturation region, but right now we are doing this for this case, and VDS was 0.07, and from this one we'll get the similar one. So this is 65 into 10 to the power minus 6, which will be equals to mu n 69 into 10 to the power minus 9, 30 times 2.5 minus VTH 0.07. The best thing will be to just subtract these things. So if we are subtracting this, it will be like this: 10 to the minus 6 subtraction. Let's say it's 1 and it's 2. So subtracting 2 from 1, we'll get mu n 69 into 10 to the minus 9 multiplied by 30 into 0.07, and it will eliminate this, so it will be 2.5 minus 1.5. So the values will be let me first write it down. So mu n equals to 40 times 10 to the power of minus 6 divided by 69 into 10 to the power of minus 9 multiplied by 1 by 30 into 0.07, and 1 by 2.5 minus 1, so it will be 1, right? So we just have to put the values. So Let's first cancel this out. 30, 30, and this thing, I guess, so better to calculate this. 40 divided by 30 divided by 0.07 divided by 69 divided by 10 to the power of minus 9 multiplied by 10 to the power of minus 6. So this is nearly 276.05. 276.05. So the value is this 522 something. So let's write it like this. So the value of mobility is in centimeter square per volt second, I guess. Okay, sorry. So let's move on to the next one. Consider an N MOSFET with VGS of 1.8 volts, W by L 4, mu and Cox of 17 to 10 to the power minus 6 ampere per volt square, VTH of 0.3 volts, and channel modulation parameter of 0.09 volt inverse. Now we know that the MOSFET is operating in saturation. We have to find out the value of drain conductance. What is the value of drain conductance in microsiemens? So the basic equation is nothing but this, right? Mu n Cox by 2 W by L VGS minus VTH whole square. But as they have mentioned the channel modulation parameter, so that's why it will be 1 plus lambda into VDS. That's it. So we just have to do this and we'll get the value. So try to solve this. Just put the values and you will get the answer. This is a basic differentiation, so maybe I'll do this. So this is nothing but mu n Cox by 2 W by L VGS minus VTH whole square multiplied by lambda. So we know all the values here. So how much was this? Was 70 times 10 to the minus 6 by 2. W by L was 4. VGS is 1.8 minus VTH is 0.3 whole square multiplied by 0.09. So we'll just have to put the values. So as they have already mentioned to like get the value, so we'll just remove this part, I guess. So 35 times by 4, 35 times by 4, 1.8 minus 0.3 whole square multiplied by 0.09. So it is nothing but 28.35 into 10 to the power minus 6 Siemens, and this will be 28.35 microsiemens. So this is it, and I had a few problems remaining, but maybe we'll conclude today's session here. And from the next, from next week, so we have already learned about the MOSFETs and how to characterize these parameters, how to characterize these devices, and how to extract the parameters directly from the equation and also from this. So from here onwards, so what we'll learn is that how to utilize them in circuits, and further few improvement in this structure and everything. So we'll move towards TFTs or thin film transistors as well. Thank you for attending today's session.
I have a request.
Ah, sure,
So,
sure.
uh, um, so you are uploading the videos of these sessions, right?
Ah, yes.
But I think last two sessions were not updated properly. The wrong videos have uploaded,
Okay. So,
and I have not checked the previous one, so I don't know. But at least last two sessions are not properly uploaded.
last two, you mean BJT and MOSCAP, right?
Yes.
Ah, okay, okay. I'll recheck them surely.
Yeah.
So
Thank you.
BJT one and the MOSCAP one, right? So that will be lecture 8 and 9. Okay, okay. I'll surely check them. Sorry, lecture
Yeah.
7 and 8, right?
Seven, and eight. I have to check, but last two sessions
Ah, okay,
were
okay.
not.
Surely, surely. I'll check them. I'll check them.
Thanks.
So you were talking about the videos or the slides?
Uh, s- I think you uploaded the link of YouTube this session, right? Complete session.
So I have uploaded both. So I have uploaded these slides, which I am just doing this in this class and these things, and also the video as well.
Oh, I did not check the slides, but I
Okay, so you were talking about the
definitely
videos. Okay,
videos.
okay,
Yeah.
okay. I'll check them. So you are
Okay.
saying that they are misplaced with some other videos or something like that.
Yeah, I think short duration videos and all.
Oh, okay, okay.
That
I'll
has
check
no.
them. I'll check
Yeah.
them.
It
Yeah, sure, sure,
okay.
sure.
Thanks.